Good afternoon, class. We are looking at Chapter 2, Limits, and here's Section 2.2, Limits of Functions at Infinity. We covered limits of sequences and now limits of functions at infinity. Here's the summary of what we covered. A sequence is an ordered list of numbers, or function f whose domain is the set of natural numbers. Natural numbers are 1, 2, 3 to infinity. Limit refers to the long-term behavior of a sequence, i.e., what happens to a sub n of a sequence in a long run. The limit of a sub n as n approaches infinity equals n. We say that a sub n converges to n. If that limit is infinity, negative infinity, or DNE does not exist, we say the sequence diverges. And to find limits, simply plug in and observe. A couple of theorems. The limit of r to the power of n as n approaches infinity depends on the value of the base r. If it's between -1 and 1 is 0. If it's 1 is 1. And if it's larger than 1 is infinity. Another theorem is that the limit of 1 over n to the power of p as n approaches infinity is 0 for p being larger than 0. A geometric sequence, when we add them up, becomes a geometric series. S sub n is the summation of a r to the power of n minus 1 from 1 to n, which is a plus ar squared, and it continues. Becomes a times 1 minus r to the power of n over 1 minus r. If the value of r is between -1 and 1, we said, this limit becomes 0. So this goes to 0. And the answer is the limit of S sub n as n goes to infinity is a over 1 minus r. And to solve a geometric sequence, recursively b sub n plus 1 is r b sub n, and explicitly is b sub n equals b sub 0 r to the power of n, or a r to the power of n. Dealing with patients, where we add a constant at a time step, b sub n plus 1 is r b sub n plus c. The solution becomes the same thing that we had here, b sub n equals b sub 0 r to the power of n, and we add this term 1, c times 1 minus r to the power of n over 1 minus r, and a is the same as b sub 0. And now, here's the summary of section 2.2, limits of functions at infinity. Definition of a horizontal asymptote, short HA, of the curve y equals f of x is y equals L if the limit of f of x as x approaches negative infinity is L, or the limit of f of x as x approaches infinity is L. So, these functions you may remember, the limit of 1 over x as x approaches infinity is 0. The limit of 1 over x to the power of a p as x approaches infinity is 0 for p larger than 0. We did this for sequences, which means in both cases, the horizontal asymptote has the equation y equals 0. Now, an exponential format, y equals b to the power of x, where b is larger than 1 is called an exponential growth, looks like that. And when b is between 0 and 1 is an exponential decay that looks like that. For example, e to the power of x is an example of exponential growth. The limit of e to the power of x as x approaches minus infinity is 0. The limit of f of x as x approaches infinity is infinity. In this graph, the limit of f of x as x approaches minus infinity is infinity, and the limit of, for example, the function e to the power minus x, which is a decreasing function, exponential decay, the limit of e to the power minus x as x approaches infinity is 0. And these two refer to the fact that the x-axis or y equals 0 is the equation of a horizontal asymptote. This is a cube function, y equals x cubed. The limit of f of x as x approaches minus infinity is minus infinity. The limit of f of x as x approaches infinity was infinity. I hope you remember that this was discussed in algebra, known as the end behavior, everybody. The end behavior. So that's the synopsis of what we are going to cover. We want to take the limit for this example, the limit of 3x squared minus x minus 2 over 5x squared plus 4x plus 1 as x approaches infinity. And basically, we've discussed the technique when we dealt with the sequences. This is a fractional format, more specifically, a rational function. X is approaching infinity. We divide by highest degree term in the denominator, namely x squared. And we make up 3 fractions for the top, 3 fractions for the bottom, and we get this one. Now, I want to discuss the limit laws here and what you can do as far as skipping some steps. First and foremost, let's discuss this limit laws. Limit of a fraction is limit of the top over the limit of the bottom. And then you distribute, and the top gives you 3 pieces, the bottom gives you 3 pieces. Since x is approaching infinity, this one, this one, this one, this one, they go to 0. And these two are just a constant 3 over 5. And what you can do, and of course, it becomes 3 over 5. What you can do, as far as I'm concerned, right here, you can come to this step. You can skip the other steps if you like. If we look at the graph of y or f of x equals 3x squared minus x minus 2 over 5x squared plus 4x plus 1, looks like this, which indicates this line y equals 0.6 or 3 over 5 is a horizontal asymptote. First of all, horizontal asymptotes should be really in a dashed line because it's not part of the graph. Secondly, if you take the limit of the same function as x approaches minus infinity as the graph indicates, and you can work it out, it's 3 over 5 because, again, you have to divide by x squared. The same technique here. And this point is the point of intersection between the graph and the horizontal asymptote. Doesn't happen always, but happens sometimes. The methodology is to set this one equal to this number and solve for x to find the point of intersection. Just in case I wanted to mention a couple of things from algebra. Infinite limits at infinity. The notation limit of f of x as x approaches infinity is used to indicate that the value of f of x, the values of f of x become large as x becomes large. Similar meanings are attached to the following symbols. The limit of f of x as x approaches minus infinity is infinity. The limit of f of x as x approaches infinity is minus infinity. The limit of f of x as x approaches negative infinity is negative infinity. And they are all known as the end behavior of the function in algebra / pre-calculus. All of these functions, the limit of f of x as x approaches infinity is infinity. That means you're dealing with the first quadrant as the end behavior. Granted, some of them are getting there much faster, but nevertheless, all of them have the same limit as x approaches infinity is infinity. Again, reminding you of the cube function, y or f of x equals x cubed. The limit of f of x as x approaches infinity is infinity. And the limit of f of x as x approaches negative infinity is negative infinity. That means the end behavior takes us to the first and the third quadrant. So this is just to remind you of what we have seen as far as various graphs are concerned. Find the limits. How do we find the limits? To find the limit, just plug in and observe. So what happens when you plug in and observe? You may get to a number. You're done. When you take the limit, you may get a 0 over some number, 0 over a number other than 0, 0. You may get to some number over 0, which is either positive or negative infinity. You have to figure out the sign. But in calculus, most of the time, we get what's called indeterminate forms, which means when you take a limit, you get 0 over 0, infinity over infinity, infinity minus infinity. And indeterminate form means we don't know what the answer is. We have to investigate it further using our algebraic technique. So in short, indeterminate forms means more work. You can't assume this is 1 or this is 1 or this is 0. It's not the case, class. Indeterminate forms. We want to find the limit of 5t plus 7 over t squared plus 2t minus 1 as t approaches infinity. This is a rational function. T approaches infinity. So how do you approach that? You plug in. If you plug in, you get 5 times infinity plus 7 is infinity. Infinity squared plus 2 times infinity minus 1 is infinity. You get infinity over infinity. And the technique is to divide by highest degree term in the denominator t squared. So we are going to divide every term by t squared and simplify each term accordingly. This is 5 over 2, 7 over t squared, 1, 2 over t minus 1 over t squared. And all of this, because t goes to infinity, everything goes to 0 except 1. So this is 0, so is this one, so is this one, so is this one. 0 over 1 equals 0. What about this case? Plug in, you get infinity squared plus 2 times infinity plus 7 is infinity. The bottom is 5 times infinity plus 7. It's infinity. And infinity over infinity is indeterminate. Because this is a rational function, because t is approaching infinity, you divide by highest degree term in the denominator, t. Divide everything by t. So what do we get? The limit as t approaches infinity of t plus 2 plus 7 over t over 5 plus 7 over t. And since t approaching infinity, you replace it. If this is infinity, you write it. This becomes 0. This becomes 0. Infinity plus 2 is infinity. Over 5 is still infinity. Infinity over 5 or 5 billion is infinity. Infinity plus 2 or plus 20 billion or minus 20 billion is still infinity. It's a concept, everybody. Limit of the square root of x squared plus 1 minus x as x approaches infinity. If we plug in infinity squared plus 1 is infinity, square root of that is infinity, infinity minus infinity. Please understand again, infinity times 2, infinity to the second power, infinity minus 10,000, square root of infinity, infinity squared, they are all infinity. So, what is the technique? This is a square root. Anytime you have a square root, the technique is using the conjugate. The conjugate of a minus b is a plus b. This is a plus b, everybody. The conjugate of a minus b is a plus b. As you know, the product is a squared plus b squared. So over here, the conjugate for this expression is the same thing plus x. We are going to multiply by the conjugate. Now the question is, can I multiply by conjugate and let it go? The answer is absolutely not, because you just can't multiply by anything. You may multiply by 1. So what do? We multiply and divide by the same thing. We multiply and divide by the same thing. This expression, everybody, is 1, and you can multiply by it. So you can extend the fraction bar. You multiply these two. This is a minus b times a plus b. It's a squared minus b squared in the numerator. The denominator is just that. This comes out, becomes x squared plus 1 minus x squared, and these two cancel each other. If you plug in infinity, remember this becomes infinity, this is infinity. Infinity plus infinity is infinity. 1 over that is 0. Okay? So this happened to become 0. We want to find these limits. The limit of a 12 over 4 plus 3 e to the power minus t when t approaches infinity. You plug in, and e to the power of minus infinity is 0. E to the power minus infinity is 0, because I'm reminding you, a to the power of minus m is 1 over a to the power of m. So e to the power minus t is 1 over e to the power of t. So 1 over e to the power of infinity means 1 over infinity means 0. 12 over 4 is 3. the limit of a 5 plus e to the power of t over 4 minus 3 e to the power of t as t approaches infinity. In this case, if we plug in, what do we get? We get 5 plus e to the power of infinity, which is infinity, over 4 minus 3 times e to the power of infinity. This is infinity times negative becomes negative. So the bottom is negative infinity. Yet we are dealing with an indeterminate form. So we have to use our algebraic techniques. What is the algebraic technique? This is not a rational function, but it is still a fractional format, and t is approaching infinity. So we are dealing with a fractional format. T is approaching infinity. When it's a rational function, we divide by highest degree term. When it's not, we divide by highest value in the denominator, which is e to the power of t. Divide everything by that. You cannot say highest degree. Okay, it's not a polynomial to say that. So highest value is e to the power of t, and simplify. This becomes 1, this becomes -3. T is approaching infinity. This goes to 0, this goes to 0, positive 1 over -3, meaning -1/3 is the final answer, everybody. The limit of x squared minus x as x approaches infinity, if I plug in, I get infinity squared, which is infinity minus infinity. And again, that's an indeterminate form, which requires our algebraic technique. In this example, the technique would be factoring the x out. Now, if I plug in, I get infinity times infinity minus 1. Again, infinity minus 1 or minus a billion makes no difference. It's still infinity. The product of infinity and infinity is still infinity. Previously, we ended up with 0. Now we have infinity, and in some cases, we may have completely a different answer. The limit of x squared plus x over 3 minus x as x approaches infinity. What happens if we plug in? We get infinity squared plus infinity, which is infinity, 3 minus infinity, which is negative infinity. So we get infinity over negative infinity, which is again an indeterminate form. We are dealing with a rational function. And x is approaching infinity. We need to divide by highest degree term in the denominator, namely x. And so, if you plug in infinity, you get infinity plus 1. Over here, you get 0 minus 1. And here's what I want you to pay attention to. The top is infinity. The bottom is a negative number. Therefore, the answer is negative infinity. That's the only thing that you want to be careful of. Example 4, the Pacific halibut fishery has been modeled by the equation b of t equals 8 times 10 to the power of 7 over 1 plus 3 e to the power of negative 0.71 t, where b of t is the biomass, the total mass of the members of population in kilograms at time t. Part A, what is the limit of b of t as t approaches infinity? Part B, what is the significance of this limit? So according to part B, they just want us to take the limit of a b of t as t approaches infinity which means they want us to take the limit of this expression as t approaches infinity. As you know, we plug in and we observe. So if we plug in, what happens is e to the power of negative exponent. And that one becomes 0 because t is approaching infinity. Again, reminding you the reason for that. A to the power of negative m is 1 over a to the power of m. E to the power of minus t is 1 over e to the power of t. So this one is 1 over e to the power of positive 0.71t. So it makes the denominator infinity. 1 over that is 0, 3 times 0. And so the answer is 8 times 10 to the power of 7 units kilograms. What is the significance of this limit? What does it mean? In a long run, the Pacific halibut biomass will be this much. 8 times 10 to the power of 7 kilograms, which means 8 with 7 zeros, which means 80 million kilograms. That's the meaning of it. Example 5. The previous one was 4. So just we're going to move on. So here's the question, everybody. A tank contains 5,000 liters of pure water. Brine that contains 30 grams of salt per liter of brine is being pumped into the tank at a rate of 25 liters per minute. Show that the concentration of salt after t minutes in grams per liter is B of t equals 30t over 200 plus t. So what they want us to show is if this algebra is correct, we want to go over that and prove the algebra for that, which has got nothing to do with calculus. It should be fairly simple. So since they're talking about concentration of salt, grams per liter, that means the amount of salt over in grams over the liters of liquid. So B of t is salt in grams over liquid in liters. That's what they are asking us to come up. So according to this, 25 liters per minute of brine is added. That means after 1 minute, we are adding 25 liters of brine to this liquid pure water. After 2 minutes, 50. After 10 minutes, 250 liters of brine is added. After t minutes, 25 times that number, t. So 25 times t liters of brine is added after t minutes. Brine has 30 grams of salt. So 1 liter of brine has 30 grams of salt. So for example, if we have 10 liters of brine added, we have added 10 times 30 grams of salt. If we added 100 liters of brine, so 30 times 100 or 3,000 grams. But we have added how much? 25 times T liters. So how much of salt do we get? 30 times 25 T. So after T minutes, the amount of salt added should be 25 T times 30 grams. So what is the amount of salt? 25 times T times 30. That means 750 T grams. You're just multiplying these two numbers, and that is the numerator. What about the amount of liquid? We've added this much to 5,000 liters of pure water that we already had. So this was there already. We added this much. So the numerator is this number, 750 T and grams, and the denominator is this number, 5,000 plus 25 T liters. We notice everything is divisible by 25. We are going to factor the 25 out from the top as well as the bottom. And when we simplify, we get exactly what was given. So we proved this is the case. So this is algebra. Part B says what happens as t goes to infinity. Simply put, take a limit as t goes to infinity. Now it's calculus. If I plug in, I get 30 times infinity over 200 plus infinity. I get infinity over infinity. This is infinity over infinity indeterminate form. The technique is to use algebra. We are dealing with a rational function, and t is approaching infinity. You divide by highest degree term in the denominator. So we divide everything by t and simplify. So the limit as t approaches infinity of 30t over t, 200 over t plus t over t, this is 30, this is 200 over t, and this is 1. As t approaches infinity, this goes to 0. 30 over 1 is 30 grams of 30 grams of salt per liter. Now, what is important is to understand the effect of that, the meaning of that, what's going on. We got the same number here. Brine contains 30 grams of salt per liter of brine, and we have, although we have 5,000 liters of pure water, we still get the same number. Why is that? So, the idea is that if you are adding brine just a little bit, so you do get some sort of a concentration, but if you keep on adding indefinitely, that's the meaning of t approaching infinity. You continue so much so that in a long run, all the liquid turn into brine, meaning not that this one turned into brine. This really has no effect. It's so small compared to the amount of brine that has been added over the course of t approaching infinity, that in a long run, all the liquid turn into brine.